Good morning and welcome to today's electronic design webcast. Our topic today is tackling PCI Express and Ethernet increasing bandwidth demands, and it's sponsored by TTI and 3M. I'm Alex Pault with Endeavor Electronics Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box and a member of our team will assist you. You can also click on the question mark Help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will be following the main presentation. And please feel free to send in your questions at any time. To do so, all you have to do is simply type your questions into the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. So, let's meet today's speaker. David Forsyth is a Senior Global Portfolio Manager in the Electronic Materials Solution Division at 3M, the 3M company. His career started as a manufacturing engineer and transitioned to product marketing. In his current role, David is responsible for twin axial cable products for high-speed applications and industrial connector products. He's accompanied by Mark Latang and Dennis Doy, their senior application engineers for the company, who will help us answer your questions after this presentation. As I pointed out, you can submit your questions at any time. We'll answer them at the end, and the ones we cannot answer, we will send you email responses. So let me turn things over to our presenter. David, the floor is yours.
Thank you for that introduction, and now let's get started. Today we'll talk about bandwidth market trends. I'll go into the PCIe technology and a little bit of the overview of the organization. I'll speak a little bit about TwinX products by 3M. We'll speak about the Ethernet standard in the organization, and then I'll speak a little bit about 3M's products for that market space. So let's get started. When we look at the digital infrastructure, we see that there's three elements according to Equinix: the digital core, the digital ecosystem, and the digital edge. And what this really speaks to is that at the digital core, we see enterprises migrating away from on-premise data centers to cloud data centers. And this is, as you'll see in later slides, allowing them to achieve economies of scale, efficiencies in operations, and serve their customers better. And then as we look at the ecosystem itself, the cloud platform allows the enterprise or the business to then focus on what is listed here as XaaS. And that's really anything as a service. And typically we think of software as a service. And what that allows them to do is provide services that they can generate revenue on, software that they can generate revenue on, and really serve the various segments of the industry. And then where we see a lot of new innovations from the 3M perspective is looking at the digital edge. So enterprises are looking at data centers to provide their computing services. And then as you look at providing those services to the user, there's a fixed amount of network bandwidth. And with the digital edge, we're moving the data, closer to the user. So 5G networks are allowing us to compute faster, communicate faster, and digital edge brings data centers closer to the users. And so as we evolve with faster computing, we see the computing power itself moving to what we're calling the digital edge. And when we look at technology trends for those kinds of devices, this is just a brief history of the PCIe standards. And as we look at the 2000s, PCIe 1 evolved, or the major device that brought us aware of these communication and processing capabilities was the BlackBerry pager. And that went from a pager using your cell phone to a pager with instant two-way communications on a 3G cellular network. And that you can see in each of these evolutions of the PCIe standard, from PCIe 1, 3 through now 5 and 6, that each generation of device, with the BlackBerry, the iPhone original, up to, I think, just recently released the iPhone 14, we see that the devices are communicating faster with the 3G, 4G, and now 5G network. You heard me mention earlier in the previous slide, 5G networks really supporting faster on-demand data and services to the user through their user interface and device of a cell phone. And that typically for most of us is an iPhone, and in some cases might be an Android or Google phone that you're using. And so the data that you're using on your device, the services that you're using, typically that would generate or emanate from a data center. And you heard me speak just a moment ago about data centers evolving from on-premise to cloud computing. So we're seeing that migration as well to cloud computing, edge computing, and then moving towards local processing or networks of IoT devices. We see that the chip sizes are decreasing as well. So they're able to put more transistors on a single chip to increase the computing power. And that's being supported with the local devices, with streaming TV being able to process that video and stream that video. Gaming has really emerged during COVID as a growth segment where high-speed computing and processing is required. And then with each of those evolutions in device computing power, network speed, we see that the data center infrastructure also is increasing. So the PCIe standards have evolved from 1 to 6, and the Ethernet speeds have evolved from 10 gigabit Ethernet to 100 gigabit Ethernet in the early 2010s. And now we see customers, enterprises implementing 400 gigabit Ethernet. And then we even see early adopters in hyperscale implementing 800 gigabit Ethernet. So the message here with the evolving standards is smaller, faster, higher bandwidth devices to give us the data we need when we need it. If we look at cloud migration, there's various aspects of cloud migration, and the companies that you would typically hear about providing these services, Microsoft, Amazon, Cisco, Google, IBM, all of these companies have developed cloud computing infrastructure. So they've developed a data center, developed their own economies of scale, and are now offering those in a public, private, or some type of hybrid environment so that enterprises can offload their on-premise data centers and allow these companies that I just mentioned to host and provide that service for them. And as we look at the accelerated migration, many of us have been working from home over the last 2.5 years. And what that has driven is the need for computing that is really scalable, agile, so that as services or bandwidth requirements increase, the network, the data center scales with that. So you can scale up your capacity with increasing demand, and you can scale it back with decreasing demand. And that's a key functionality that many enterprises are enjoying with cloud computing, so that the infrastructure that you have traditionally on premise that can't scale. You have a fixed amount of capacity that you've already invested in, and now with cloud computing, that service is now available where you can increase and decrease your capacity. Additionally, we see features of security, cost savings, flexibility, and scalability that I just mentioned. That's because you have a specialized provider now managing your IT infrastructure versus the enterprise managing that IT infrastructure. And an example that I'll bring up here is FedEx. If we look at FedEx, FedEx will be closing all of their data centers or retiring their mainframes by 2024. We haven't spoken about that, but a lot of the traditional data center services were provided by mainframes. And what we see today is that servers that are CPU based, x86 based, are really replacing these mainframe computers and providing better performance at higher efficiencies. In FedEx, in migrating their data centers to the cloud, anticipate savings of over $400 million by 2024. So for an enterprise, those kinds of cost savings with the benefits that we've spoken about just a moment ago is really compelling for more and more companies to move to the cloud. When we look at other potential applications other than your email, your hosted office, and your social media, we really see AI or artificial intelligence and ML or machine learning as driving the increasing demand for data centers. And why is that? AI, with the computing power available today, allows us to train through machine learning the servers to analyze tremendous amounts of data, calculate the data at an accelerated rate, and provide insights that would take us a significant amount of time to do if we weren't using these tools. So we see 51% of enterprises have implemented or plans to implement AI. 25% of those companies have already implemented AI. And so again, we see this as how do we make better decisions with the data that we have? And AI is the tool for that. And if we look at the forecast for spend here and business value, we see by 2030, 44% will use AI and machine learning in some capacity within their enterprises. So that's a significant use of this technology and tool to develop insights with the tremendous amount of data that we're developing. When we look at the global forecast for the industry in the interconnection, we see that globally, the industry from 2020 to 2024 is growing at a CAGR, or compounded annual growth rate, of 44%. That is tremendous, tremendous growth. And you can see from this slide from Equinix that the service providers or the industries driving that growth, we see telecommunications with 45%. We see cloud and IT services at 45% and hyperscale providers at 42%. So even though the scale here shows that there's variations in each of those, the growth rate for each of those service providers is still tremendous. And then if we look at the enterprises that are using those services, we see banking and insurance, we see securities and trading, manufacturing, leading that volume and all growing at over a 40% CAGR. So let's take a moment now and I'll review some of the PCIe specifications and standards, and then the 3M products that are associated with those. So the PCIe standard was founded in 1992. It's an association of industry companies, over 800 of them, that are all working towards a common goal, a common specification for performance. And this group looks at defining the specifications for performance, looking at future technology trends and how the technology of PCIe Express should evolve to support those future applications. And one of the key features of the PCIe standards is that each new generation is backward compatible with the previous generation. And you'll see in a couple moments that I have some slides reflecting that. And so what this allows us to do, similar to things that we know on a consumer level, like USB, like lightning cable, allows the interoperability of devices really at an industrial level. And so the PCIe SIG, this organization that defines the PCIe Express standards, looks to double the bandwidth of this interconnect technology every 3 years. And we can see that PCIe 5, the specification for that was released in 2019. And then PCIe 6, the specification for that launched in 2022. And then there's plans for PCIe 7 to launch to the market or release the spec by 2025. And so even though I said launch, it's really the release of the specification in those time periods that allow the industry to start looking at their hardware designs and then designing hardware that conforms to that spec. And so you might see adoption of those specifications in devices, seeing the real life performance of those maybe a year to 2 years after the introduction of the specification. And then when we look at the generations, you saw in a previous slide that there's the evolution of each of the generations that you see along the top, generation 1, 2. So that's really PCIe 1, PCIe Gen 3, 4, etc. And the year of release with each one of those. You can see that the bandwidth is doubling in each of the standards. And really key is backward compatibility, so that if you're designing a Gen 5 card or device, that can be plugged into a Gen 3 system. And you'll see on the next slide what that means. Even though it's backwards compatible, you still need to consider the performance trade-off with that. But that device will be able to function in an earlier generation device. In terms of modulation, this is important where up until Gen 6, NRZ was used. That's non-return to zero. And with the implementation of Gen 6, the modulation has switched from NRZ to PAM4, so pulse amplitude modulation with forward error correction. And so that allows us to transmit data faster and then compensate for any errors within the channel. And then we see for Gen 7, the plans for modulation will be the same using PAM4. When we take a look at potential target applications for this, you can see for PCIe 4 and 5, the application that you see in the graphic is really visual. PC gaming, you think about the PlayStation, you think about the Xbox, those might use a proprietary CPU. In the case of PC gaming, that's using an x86 processor. And what that allows us to do using an x86 processor, which supports a faster bus speed, is implement a PCIe 4 or PCIe 5 peripheral device standard. And the reason why that's important in PC gaming is you can see from the LEDs, the keyboard mat, the mouse mat, the LED lights for the fans. Not only is performance important and spending significant amount of money on the GPUs, but those GPUs, the gamer wants that GPU to be a highlight of their gaming rig, just as you see here. And using a PCIe bus, you can move that GPU from one portion of the motherboard to another so that it really becomes a aesthetic as well as a functional part of the hardware. And so gaming is really prominent in driving some of the adoption of this standard, driving the volume for the CPUs. We see that the servers that are x86 based are moving towards supporting a PCIe 4 and a PCIe 5 standard. We see more corporations designing systems that will be future-proof. So if they're designing it today and they need to upgrade in the future, can the hardware they're designing be compatible with PCIe 5 devices that'll come out in the future? And that's part of that backwards compatibility that I spoke about a moment ago. We see HPC also driving these faster standards with the need for computing at higher speeds and looking at millions or trillions of instructions per second. These applications are really geared towards using a PCIe bus with Gen 4 or 5 capability. When we look forward at PCIe 6, we see these hardware and applications evolving. Again, similar applications, faster speeds, more intensive applications. And we also see the emergence of industrial, automotive, and potentially military and aerospace applications where more compute power is needed at faster speeds. And then looking forward into the crystal ball for PCIe 7, we see that the need for data-intensive applications and markets will still drive a faster internal network or internal bus requirement with PCIe 7. And then we also see that 800 gigabit Ethernet will be needed to support the structure of the PCIe 7 protocol. And when we look at PCIe 6, 4, and 5, I didn't mention it here in the slide, we see the evolution of as well with the Ethernet from 100 gigabit to 200 and quickly to 400. I mentioned a little bit earlier about the backwards compatibility. So when we look at the PCIe standard and we look at the bandwidth and backwards compatibility, you see on the left that we're looking at each generation of the specification and the speed. Across the top of the table, we're looking at the various form factors that are available, a by 1, a by 2, up to a by 8 and by 16, which increases the number of channels per connection. What we see is that each of these is compatible with the previous generation, but if you're designing, as I mentioned in the previous slide, a PCIe 5 peripheral device, and you're going to use that in a PCIe 3 system where the CPU and bus only support PCIe 3, your interface is going to default to the slower or the previous generation speed. So the PCIe 5 device, even though it's compatible with the PCIe 3 motherboard, will switch from a 32 gigabit per second device to a 8 gigabit per second device. And so you'll still have the functionality, just at slower speeds. So let's take a look at the 3M brand twin axial cable solutions that are geared towards PCIe protocols and supporting the faster speeds of PCIe 4, 5, and 6. You see on the right a rendered drawing of a server, and what you see there in the blue lines are the DIMM slots, and in between the DIMM slots you can see the CPUs, and the light gray illustrations with the darker gray or black terminations are illustrations of how you might use a 3M brand twin axial cable. So our cables are very flexible. They're foldable. You can see that these cables are bent at 90-degree angles, bent at 45-degree angles. Because it's thin and flexible, we can route in between the DIMM slots. We can route in between the fans. Our cable orientation is parallel to the airflow so that we're taking advantage of the minimal space in these dense servers. We're routing parallel to the airflow, which maximizes your cooling efficiency. And we're doing this without compromise in signal integrity. So when we bend, fold, and route through these complex areas, there's a negligible impact on SI performance. So how do we do this? If you look at the illustration on the right, in the upper right corner, the silver cable that you see connected to the PCB is the 3M brand twin axial cable. And we manufacture this cable and laminate a continuous shield over the high-speed pairs as well as the grounds. And you can see there the grounds are placed parallel to the high-speed signal wires. And that dimension of the placement of the high-speed pairs and of the ground is precision controlled in our manufacturing process. So the combination of the precision controlled placement and dimensions of the high-speed pairs of the ground, plus our continuously laminated shield, allow us to create a cable that's thin, foldable, and flexible, and will not have a degradation in SI performance as you route it and bend it within the server. And because our cable is precision formed and manufactured in our factory, that allows us to precision terminate it. So we can strip the insulation away, we can bend it, form it, and then solder it to the PCB, all with uniformity, which increases your efficiency and quality of your devices. And if we look at how a traditional or competitive twin axial high-speed cable pair is formed and manufactured, you can see that the shield shown here on the lower right in the light purple is spiral or longitudinally wrapped around the high-speed pair and the grounding cable. This is a typical construction. There are other constructions available in the industry, but when this happens, the SI performance is compromised so that it's not resonance-free like the 3M brand twin axial cable. In addition to that, as you wind in this method, this cable becomes thicker and less flexible, so that if you recall the rendering that I showed in the previous slide, this cable cannot be bent and formed within your chassis in the same fashion that the 3M brand twin axial cable can. So we provide a cable that is better in terms of routability, bendability, foldability, while maintaining SI performance and fitting into your specific server application. So the cable can be terminated in various form factors. And what we show here is a table of various 3M products with various form factors, all using the 3M brand twin axial cable. So the first three on the left, 3M Slimline, Mini Slimline, and Compact Slimline, all conform to the SFF 8654 specification. So these are available in similar to the CHEM connector that I mentioned earlier on the PCIe SIG in various number of lanes, 4, 6, 8, or 12. And as you look at these, we've evolved our product to the needs of our customers. So the Slimline assembly, we reduced the height and called it Mini Slimline because of those condensed spaces, and Compact Slimline reduces the width. All still compatible with SFF 8654, which is the PCIe SIG specification, but evolving the product to the needs of our customers in the dense server environment. And what we're seeing in the middle is the need for a low profile IO assembly. This is compatible with industry standard board mounts and provides a different form factor, slightly better performance when we look at PCIe Gen 4 and the future. And then we also have a multi-channel IO termination that you see towards the right. And that's compatible with the SFF TA 1016 standard. And so this provides the industry with a uniform connector that can mate to a board mount and have the performance of PCIe 5. The last two columns on the right, the scalable high-speed assembly, is better known as Gen Z in the industry, and most recently SFF TA 1020 or 1002. This started as a open source consortium trying to develop a standard connector that the industry could use that would not be proprietary. So I mentioned Slimline, some know it in the industry as SlimSAS as an open standard, and the market started to migrate towards fragmented proprietary interfaces that I just mentioned, the low profile multi-channel IO. And so the industry saw a need to standardize and created the Gen Z connector. And then that was donated by the Gen Z consortium to PCIe SIG and became SFF TA 1020 or also 1002. So that's available in the same number of lanes that we talked about before, as well as 16, but their nomenclature is slightly different in that these form factors are called chiclets, 1C, 2C, 4C, but that corresponds to the traditional number of lanes by 4, by 8, by 16. And then lastly, more aligned to the PCIe SIG Chem connector is the 3M extender product family. And so this is a connector that's compatible with and conforms to the PCIe Chem standard and allows you to connect in the illustration that I had previously with PCIe gaming, a peripheral device using a Chem connector on the board to a peripheral device located off the motherboard. Excuse me. So I'll now move to the Ethernet standards body and describe a little bit about the Ethernet standard and the organization that supports that. So IEEE is the Institute for Electrical and Electronics Engineers. It was founded in 1963, and it is more of a Ethernet standard for external devices communicating from the server to the switch and then the switch out to the network. Many of you in your homes have Cat4, Cat5, Cat6 cable that performs to an IEEE standard. And so these standards are typically numbered IEEE 802.3 dash or dot another number. And we'll review a little bit how those standards apply to data center applications. When we look at the market, similar to how we looked at the market for PCIe, we see the market for Ethernet, the majority of it being 100 gigabit Ethernet. And when we look at the evolution of speeds to faster speeds, we see that in this graph on the left, that 200 gigabit Ethernet really never took off in terms of customer or data center adoption. And part of the reason is that 400 gigabit Ethernet really came on board fast with the capability of higher bandwidth in a shorter amount of time than 200 gigabit Ethernet. And so as companies looked at the benefit of moving to 200 and then another step change to 400, many of them opted to move from 100 gigabit Ethernet directly to 400. And depending on the application of the hyperscaler or of the enterprise, we see that the adoption from 400 to 800 is moving even faster. But you see in this graph that the industry is labeling 400 and greater in this graph that you see in the black area just above the 200 gigabit per second Ethernet. And so similar to PCIe, you see the adoption or commercialization year with 100 gigabit Ethernet in 2016, 419, and then emerging now in 2022 and 23, 800 gigabit Ethernet. So the industry is evolving as consumers and applications demand for us to have higher bandwidth communication. So from here, I'll mention a few of the 3M brand twin axial external cable assemblies. These are also known as direct attach copper cable assemblies, or DACs for short. When we look at the properties of these cables using the 3M brand twin-ax cable, it has similar functionality and benefits to our internal cable assemblies. These cable assemblies are flat. They can be bundled, as you see on the right, into cable bundles that can be easily organized in a rack. And you can see that by bundling them and moving them to the side, we can increase the airflow into the server, into the rack area, so that cooling is more efficient. And you can see from this illustration that by moving it, bending it, and folding it to the side, our cable has a negligible, or what we like to say, zero bend radius, so that you can bend it and fold it and route it the way you need, and does not have a minimum bend radius to maintain performance. And so that's a benefit of our cable as you route it in these dense environments. So when we look at a data center, and you can see the illustration here of a typical data center, you need to connect the network interface card to the switch. That switch could be at the top of the rack, a TOR, or middle of the rack, a MOR. What our cable allows you to do is connect that NIC at 100 gigabits per second or 400 gigabit per second to the NIC and route it in these dense environments. So you can see stacks and stacks, rows and rows of servers that compromise a data center. And all of these are really dense, highly efficient systems that would benefit from the use of the 3M DAC cable. When we look at the product family for DAC cables, we can see that 3M is developing an 800 gigabit product today. We'll have that available in the near future. Today, we have a 400 gig product using the QSFP-DD form factor. When I mentioned the various form factors in the previous table, that was for internal cables. When we look at external cables, the form factors are a little different. We have QSFP-DD, so that's double density QSFP, and that is a double density of the QSFP-28 product that you see in the middle. So that communicates at 100 gigabit per second, and then that's available in a straight cable, a Y cable, and a breakout cable. So depending on your architecture and your NIC configuration, you might connect a slower NIC to a faster switch, and these products would allow you to connect and interface to that. And then I mentioned the standards previously. When we look at the standards, the IEEE 802.3CK would be associated with the 800 gig aggregate data rate product. The IEEE 802.3CD specification or standard would be associated with a 400 gig product. And then there are a lot more standards associated with the 100 gig. So that's an SFF 8436, but really the in parallel to the IEEE would be the IEEE 802.3BJ specification or standard. And so each of these is a standard form factor using the 3M cable that's plug and play in your system. So with that, I'd like to close our presentation. Thank you for joining us today and open up the floor for questions.
Thanks a lot, David. I really appreciate that. And I just wanted to say before we got into it, it's really amazing how fast and far we've come and how the entire market has expanded to the point where we're anticipating these bandwidth capabilities and we're already planning what to do with them. You know what I mean?
Absolutely. There's lots of applications for our technology, and it's really exciting to see each of these new applications emerge.
Well, you know, and having said that, we do have some questions, so I will go to them, and we'll continue this afterwards. The first question we have here is, you showed a number of different internal cable assembly form factors. Are you able to make hybrid assemblies which combine different connectors on each end? For example, slimline to mini slimline.
That's a great question, Alex. And absolutely we can. Each of those form factors, depending on the server architecture and the pinout, can be mixed and matched, if you will. We could have a slimline termination on one end with a multi-channel I/O termination on the other. And not only can we vary the termination on each end of the cable, we can also create custom lengths of cable assemblies and then custom folding. You recall that in that graphic that I showed of a server, that most of those cables were straight line and then bent at the end towards the connection to the motherboard. And any of those cables can be custom bent, folded, and taped to fit your custom server design and where you need cable routed.
Excellent, excellent. Now, I've got two questions here that are actually linked. So I'll read you the first one, and then I'll read you because there one is basically a tee up of a question, and the other is a follow up question that allows you to answer it better. When you hear the question, you know what I'm getting at. The first one is: are you investigating fiber optic solutions?
Yes, we are. We have a product called Expanded Beam Optical, which is a interconnect that we're creating that would reduce the need for cleaning in multi-mode and single-mode ferrules. So that product is called Expanded Beam Optical, and we call it short EBO. We've developed that over the last few years, and we've sampled the large fiber optic companies in the industry and are working to commercialize that with a end customer in a data center.
Got it. Got it. Now, the follow up, which I guess is the other question, interestingly, is can you explain? The person had, I guess they must have missed that part of the presentation. Can you go a little bit deeper into the benefits of copper over fiber for less than 4 meters, which is related?
Absolutely, we can do that. And I think from a cost and performance perspective, the industry is always looking for what's the lowest cost solution that I can implement in the data center that provides the maximum amount of performance for my customers. And today, that's still copper cables. When we look at direct attach copper cables, the industry a number of years ago said that the technology had reached its limits and that optical would take over. And optical has taken over in the fabric of the network, but still going from the NIC to the top of the rack, copper is still the dominant technology solution. And as we evolve to 800 gig and maybe 1.6T, even though the reach of the copper direct attach cable is shortening, the cost performance ratio is still a higher benefit over the optical. And so much so that we see customers redesigning the typical rack configuration and moving the switch where needed to maximize the performance of the DAC cables. So that's what we're seeing, and eventually, as onboard optics becomes available, that might change. But the cost, power, thermal aspect of using copper are all still benefits that outweigh the performance of the optical and the cost.
Excellent. Now, we're almost out of time. We have time for one last question. And I figured we have other questions, and I just want to let the audience know that every question will be answered. We'll be emailing you answers to all of your questions. Unfortunately, we only have time for one, and so I figure I'll give David the opportunity to do a little bit of forward looking into the crystal ball, as it were. This question is, do you see any major changes in the PCI standard in the next 5 to 10 years, or is it just going to be enabling faster speeds?
That's an interesting question, and if I had a really good crystal ball, I probably wouldn't be on the webinar. So what we're seeing in the PCIe space is from the graph, the PCIe SIG graph, that doubling every 3 years. And eventually, we're probably going to reach the limits that CPUs have reached with Moore's Law. And when we see that, we'll probably look at onboard optics and connecting to direct attach cable, or eliminating that, if you will, and going to multi-mode, single mode. And you'll probably see something similar inside the box. Once the CPUs are capable of managing light and the signals through that with the custom processors, we'll probably see some type of migration away from copper. What that looks like in terms of PCIe and those form factors, I'm not sure of yet, but as the technology becomes available for onboard optics, I would think that we'll see some of that emerge in the PCIe space.
Well, I agree with you completely there, David. There's nothing but up looking forward just about everywhere in the electronics landscape, and it's all got to talk to each other. So I really appreciate your very insightful presentation and information and answers today. And I'm afraid we have run out of time. And as I pointed out, for those questions we didn't have time to answer, we will be getting back to you via email. I'd like to thank you all for taking the time to listen to us, and have a great day.
Thank you, Alex. Thank you, everyone, for joining us today.